Hello everybody and welcome back. Just got some time off here from work with the holidays coming up, and just got back from a little trip with the family. We went out to see the Pittsburgh Symphony Orchestra and the Mendelssohn Choir for their holiday special, and that was a lot of fun. A lot of fun. You know, all this equipment that we work on, all these stereos, no matter how good they are and how accurate they sound and everything, nothing will ever replace, going to a live performance. So anyway, I want to start out this video with a little disclaimer that if you're looking for just a repair video of the tuner on this, that's not really what I'm going to do on this video. The tuner on this works really well. So what I decided to do with this video is we're still going to be looking at the realistic STA 2200, but what we're going to talk about more is how a PLL synthesized tuner works. I've had a lot of questions asking me, people asking to kind of expound upon that and do a video on how they work. So I thought I'd take the opportunity on this one. This is a really good example to show people because all of the components are so separate and modular and easy to look at, easy to access and measure. And to be honest, this tuner is working relatively well. It's not super sensitive, and some of that has to do with the design of the tuner itself. But really what we're going to be interested in this video is kind of talking about how a synthesized tuner works, especially when compared to some of the older analog tuners that we have out there. So if that sounds interesting to you, stay tuned. And if not, there'll be plenty of other videos coming out where I do repairs and so forth coming up. I have a whole ton of stuff waiting to go on the bench. All right, so let's get started. So before we know where we're going, we kind of have to know where we've been. So let's start out a little bit on this first radio. The earliest radios that were, beyond just a crystal radio were what's called tuned radio frequency. So really, what's a radio? Well, a radio, of course, we have to have a resonant circuit that is tuned to the same frequency of the broadcast station that we want to listen to. And then it's an amplifier, so we have to make that tiny little signal loud enough to hear, and then we have to demodulate it in order to take the audio sound away from the RF. So in the early days, this is how you did it. If you notice here, you have these coils and capacitors. So this coil and capacitor together we call a tank circuit, and you can see it's coupled to this antenna. And the idea is if we adjust this capacitor so that it works in conjunction with this coil, it will resonate at a certain frequency. So we can adjust this capacitor to resonate at the frequency that we want to receive from this antenna. So for instance, if we want to receive 1 megahertz AM broadcast band, we would adjust this capacitor until this tank circuit were resonant at 1 megahertz. Now once we get this tuned to the frequency that we want to listen to, we have a tiny little signal here. So that's why we have to have an active element like this vacuum tube right here to amplify it. But it only amplifies it a tiny little bit. It's not enough. So once again, this is now oscillating at the frequency of our antenna, and we want to tune the next stage to that same frequency, so it'll only allow that frequency to pass and nothing else. So once again, we have another capacitor and another tank circuit that's coupled, magnetically coupled to this stage, and we tune it to the same frequency that we tuned this one to, and so forth. Then it amplifies it a little bit more, and then we go to the next stage and we have to tune it. So if you notice, we have multiple capacitors and multiple tuned circuits, and they all have to be perfectly lined up. If they're misaligned in any way, it'll either weaken the signal or distort the signal or it'll block the signal altogether if it's bad enough. Now you can imagine the balancing act it is, because these old radios used to have 2 or 3 separate knobs for tuning, and you had to do each one individually and make sure they all lined up. And that's why this is called tuned radio frequency. It's very awkward, very unstable, and very difficult to keep this thing tuned on frequency, because you got your vacuum tubes drifting, you have these capacitor values drifting, the outside world influences it. Even if you move your hand too close to the tubes, it would change the capacitance and it would throw things off frequency. So it was kind of a little bit of an art to be able to adjust these things. So this is the early type of radio. Okay, now everything from here we're not going to really worry about. This is where we actually, this detector is actually what removes, it's a filter that filters out the RF frequency and only lets the audio frequency pass through. Then we amplify that some more and send it out to the speaker. So that's the way it used to be many, many years ago. Now, we haven't done this for a while, but this is what it used to look like. So we're now fast forwarding a whole lot to a modern receiver. And this receiver is actually a Pioneer stereo receiver, one of the old ones like an SX450 or 550 or something like that. But it uses a process called Superheterodyne. And I believe it was Edwin Armstrong that's credited with the design of the Superheterodyne receiver. And I believe it was the RCA, Radio Corporation of America, that first patented it. But I could be wrong. Go down in the comments section and correct me if I am, because I'm pulling that off the top of my head. But here's the problem. When we have to tune those 3 capacitors all separately, it makes it very difficult to keep everything lined up. As you could imagine, it's kind of like trying to juggle. And it would be very nice if we could tune something to a single frequency and then only worry about that single frequency staying consistent all the time. And that's exactly what a Superheterodyne radio does. So what we're doing here is it's the same in the very front end to our TRF receiver. As you notice, once again, you have your antenna input, and you have your tank circuit, and you have a variable capacitor that we can use to adjust the frequency. And there's 2 separate ones, one for FM and one for AM, but if you notice, they're basically doing the same thing. Okay, we really aren't going to worry about that. So we take that, we tune it to the frequency that we want. However, you see this little dashed line here. This little dashed line actually means that this capacitor, and this capacitor are all connected together. And if you notice down here, we have a transistor. So this little FET right here, it's a special transistor that's used to amplify the RF signal. So this is an RF amplifier. And this down here is actually configured as an oscillator. And of course, when we take a coil and a capacitor and we put them together, we make an oscillator. And that oscillator drives this transistor, and it is tuned, and you can see there's fine tuning adjustments on this. It's tuned in step with this, except it is going to be a little bit higher or lower frequency than this by a set amount. Now that set amount we refer to as our intermediate frequency. So for instance, whatever this is tuned to, at least with an FM radio, this one is adjusted to be 10.7 megahertz higher. So if I have 90 megahertz here, I would have 100.7 megahertz on this oscillator down here. And then what we're going to do is we're going to take those frequencies, and we're going to filter this one more time here, but we're going to come through here, and you can see here's one end, here's the other end. They all join together, and they go into this transistor that we're going to call a mixer. Why is it called a mixer? Well, it's called a mixer because it mixes these 2 frequencies. And something happens when we put those two separate frequencies together. We actually are going to have several frequencies all on the same line here. So you're going to have this fundamental frequency, which is your 90 megahertz. You're going to have this frequency, which is the 100.7 megahertz, and then in our example here, and then you're going to have the sum of those two frequencies, and you're also going to have the difference of those two frequencies. So we're going to have 4 different peaks, or 4 different frequencies that we're generating from these two separate frequencies. They kind of beat against one another. That's why we call this, sometimes we call this a beat frequency. Now, after we do that, we want to get rid of the ones we're not looking for. We only want the difference between the two. So we just want to see that 10.7 megahertz difference. So all we do is we make another resonant circuit here that takes that 10.7 megahertz and filters it. So anything that's 10.7 megahertz within a certain width, bandwidth, or a certain range, plus or minus, gets to pass through here. Anything that is not that frequency gets blocked by the filter here, or by this transformer. And then from there it goes through some more filtering. Okay, so this is a crystal filter. And once it's done, you have down here, you have what's called an intermediate frequency. And everything here is going to always be 10.7 megahertz. No matter what we tune this to, this is going to follow it 10.7 megahertz away from it. And this is always going to look at that difference. This is always going to filter out that same 10.7. So really, everything from this point on is always the same carrier frequency. It's always, you're taking this station and you're converting it to 10.7 megahertz all the time. So every station is 10.7 megahertz by the time it gets out to here. The reason for that is once we move on from here, all of the other amplifier stages and the demodulation that takes the audio from that RF signal, all of those things are all going to be tuned to 10.7 megahertz. So we don't have to worry about them ever changing. You set them once and forget about them. It stays that way. So it's much, much more accurate and gives you a much more accurate radio that's easier to tune, because we only have this one knob with these couple of capacitors tied together to the same knob that you rotate, and it always tracks. But there you go. That's how this works. So now let's see kind of what the difference is when we go to a digital synthesized tuner. My, how complicated things can get, huh? So here's the schematic of the tuner in the STA2200. And as you can tell, there's a lot more going on in this than there was in the analog tuner. Now, this is digital in the sense that there is digital circuitry in here, but understand we still have RF going on in here, and it still is an analog signal. The RF is still analog. So it's a little bit of a misnomer to say that it's all digital. Some of the really modern gear out there uses all digital circuitry, and it works different than this, but it's based on a similar principle. We'll just leave that at that. We're more concerned about these crystal synthesized tuners. So the first thing we're going to look at is what we looked at on the last two examples. Okay, so just like the last tuner, the little Pioneer schematic we looked at, things are very similar. You have your FM RF section and your AM RF section. And the FM RF section has more parts to it, and you'll see that as we go down. But the AM section is very similar in that it uses an integrated circuit to reduce some of the component count and so forth. But one thing you'll notice that's missing from this schematic is there is no tuning gang. There's no capacitor that's linked together and that you rotate to change the frequency of this front end. Now we still have a very similar thing. We have a coil and we have a capacitor here. But we have this strange looking diode here, and this is where things start to get a little bit different with the synthesized tuners like this. So we're going to talk about these little things a little bit more here in a few minutes. Now beyond that, everything is very familiar. If we look, we still have an active element here, and it's a dual gate MOSFET, and or a dual gate FET, and what it's doing is just the same thing. It is amplifying the signal and then passing it through another resonant circuit, another RF circuit. You have another active element down here, and this is going to act like your local oscillator. So once again, it's still a superheterodyne radio in that you're going to have your RF, and then you're going to have your local oscillator that runs at the RF tuned frequency plus another 10.7 megahertz. So once again, if I tune my radio to 90 megahertz, as an example, this local oscillator will run at 100.7 megahertz. Same idea, same principle. It's just how it's producing those frequencies that's a little bit unique. So these little devices are called varicap or varactor or variable capacitance diodes. All right. And we have a few examples of those here. And just so you know, every diode has capacitance, inherent capacitance, and it is somewhat affected by the voltage. And this is kind of a phenomenon that was discovered, and these designs of diodes actually will take advantage of that. So essentially it is a diode, and we can read it like a diode. So if we connect our meter into diode mode, you can see there's a standard voltage drop across it in the one direction, just like a normal diode, your 0.7 or 0.6 volts. And if we reverse the leads, it reads an open circuit. So you can see it has a voltage drop in one direction and it blocks in the opposite, just like a normal typical diode. However, if we switch to capacitance mode, you can see this diode right now reads at about 0.8 nanofarads, or just under 1 nanofarad. So it has a fairly decent amount of capacitance in it. Okay, so I made up a little circuit here, and you can see there's our varactor diode and a little decoupling capacitor. And the decoupling capacitor is necessary to block the DC from this side from our meter circuit in the outside world. So only AC can pass through here. So our meter uses AC to measure the capacitance, so it will work. Now, of course, this is not going to be very accurate. We're just going to demonstrate the way that voltage will change the capacitance across this. So I have a little 9-volt battery. And you can see here's our circuit put together on a breadboard. And I have a 9-volt battery, and it is connected across a variable 500K pot. And it's just giving us variable voltage. And if I rotate this, you can see as I turn the pot, I can change the capacitance of the circuit. All right. Very cool, huh? So I just made a variable capacitor that varies with voltage. So if we look at a data sheet for a typical varactor diode, you can see that they come in many different shapes and they come in different ratings. So this particular one has a maximum voltage of 90 volts that you can apply reverse voltage in order to vary the capacitance. And you can see each model has a different capacitor range. So for instance, this one, if you're at 4 volts with a 1 megahertz signal, and you apply 4 volts across the capacitor, at 1 megahertz you will get about 0.8 picofarads. I believe this is in picofarads. And the capacitance ratio is determined by the capacitance with 0 volts applied across the diode versus maximum voltage, which is 90. So these are all the same ratio they use. So essentially, depending on what you need in the circuit, and you can see it goes on for multiple pages, you can get different values. Here's one that has 33 picofarads at 4 volts. So just like normal capacitors have different values, varactor diodes have different values as well. And they even come now in surface mount, which is by far the most common you see today. It's very hard to find one that's a through-hole mount now, varactor diode. They still make them, but they're hard to get. These are very common. You can order these at all the normal electronics suppliers. And you can see this one comes in a dual package. This one has a common cathode, so you can see the cathodes are tied together. But there are also other ones that have common anodes, and the diodes are facing outwards. And you can see they have 3 pins. And it's just more convenient to put these two in one package rather than having to use 2 components. So now we go back to our original schematic, and you can see these use the dual package, and these ones have the common anode, or common cathode, I'm sorry. And you can see the cathodes are tied together, and there's 2 of them, and they're applying the control voltage to the center tap there. So you can see this resistor, it's a 100K. Again, that's current limiting for this. These are very, 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 very high impedance, low current. So you don't want, you want to have that resistor in there. And you can see it goes, and it is common to all of these. So you can see there's a line going up to here, line going up to here, down here there's one coming down. They all are driven off of the same control, and we call this circuit a voltage controlled oscillator simply because the voltage that goes into that varicap varactor diode changes the capacitance, just as if you manually rotated a variable capacitor with the knob. This voltage is actually controlling the capacitance, which controls the frequency of the oscillator. So it is a voltage controlled oscillator. So whenever you guys hear the term VCO, and this is review for a lot of you, but for you new guys, when you hear the word VCO, that's what it means. It's a voltage controlled oscillator. And so now, rather than worrying about accurately rotating a control, we can very accurately dial in. As long as we have a way to adjust that voltage very accurately, we can very accurately control these oscillator circuits. Now the tricky part to all of this is getting the voltage to be able to talk to the frequency. Somehow that frequency has to be able to tell that voltage control circuit what voltage it needs to make that frequency. And you need a little bit of intelligence to do that. You need a little bit of circuitry. And this is where the synthesized PLL circuit comes into play. And this is where we see the biggest difference between an analog tuner that uses a tuning gang that you rotate and a actual synthesized tuner like this one. Now actually there were some very inexpensive tuners I've come across, like little pocket radios and things that actually do this. They just use like we just did in our experiment, they take a potentiometer and apply a voltage across it, And by varying the voltage with the potentiometer, you vary the capacitance of your oscillator circuit and you can tune the radio. And that's still a manual way of being able to tune. Now, the other way that we did it was, if you remember the Pioneer F26, or F28, I'm sorry, the F28 tuner that we did, it had a very complex encoder, optical encoder thingy that it scanned off of the tuning dial when you rotated it, and it still had a tuning gang on it, if you remember, and the tuning gang was up here, and it used the digital portion just to control the local oscillator down here. So it controlled half of it, but not all of it. This circuit actually uses this digital circuit to control the entire receiver section, both the RF and the local oscillator. So let's look at how that's done. Alright, so let's move our little camera on over here and try to zoom in a little bit, and let's see how this is all done. So again, we're trying to take the FM out of FM. Some of you will know what I'm saying. So if we look down here, there's this big integrated circuit, and it doesn't really show us much. It's just a square with a bunch of pins on it, and it is called a UPD547LC. And if you try to look that chip up, you will not find it anywhere. You might be able to find a UPC547, and you'll find out that that's kind of a programmable processor chip, but you will not find the one with the LC after it. This is a very specific proprietary component that was made by, I believe it was made by Hitachi or Motorola, one of those companies, and it was made very specifically, or maybe NEC, can't remember. Anyway, it was made very specifically for Radio Shack for this tuner. And it essentially contains all the logic that you need to produce a digital word based on what you select as the frequency to feed the VCO controlling circuit and the PLL circuit. So we just used a lot of terms. Let's break it down. So the first thing you're going to see here is these little buttons. And there's a manual up and down button, and there's an automatic up and down button. We're not going to worry about that. That's more computer tricks. We're not going to worry about that. But with the manual up and down buttons, you're going to cause this little chip down here to scroll and select through some other circuitry, select a digital word, ones and zeros, all ones and zeros, that represents the station that you want to have. Now, the first thing it's going to do is it's going to convert that through this chip, and it's going to buffer it through these transistors. It's going to convert it to a display signal that will light up the display and display the frequency that you're selecting. The other thing this chip is going to do is create, I believe, an 8-bit or an 8-bit word, which will have either 7 or 8 ones and zeros in different combinations that will equal a code that will represent the actual frequency or voltage that represents that frequency that you want. Now, so we have this code that equals the frequency. It feeds down into this little chip, and this is a more common chip. This is something that you see in just about all synthesized tuners that are out there. Without getting super modern with DSP and things like that. We're not going to talk about that. We're just talking about these synthesized. And let's see this a little closer. Okay, we've zoomed in a little bit on this PLL chip. And once again, just like that other chip, it does a whole bunch of different things. And the first thing you'll notice is I kind of bracketed these 7 pins off. These 7 pins actually show the signal that's coming from here. And remember, we talked about when I dial my up and down frequency to tune the frequency. This chip, one of its functions is to create a digital word that represents the frequency that I'm selecting with my tuning up and tuning down buttons. And it is a 7-bit word, meaning it is a string of 7 signals that are either going to be high or low, on or off, 1 or 0. So it's a digital word. It's a binary digital code, okay? And that binary code comes into these 7 pins. Now, there's a whole lot of things going on inside this chip, because what it's going to do is, based on this code that we put in here, what combination of ons and offs, ones and zeros that we put here, is going to determine what frequency, what target frequency it wants, and conversely, what voltage we want to output to our VCO, to our voltage controlled oscillator circuit up above. Now, in order to do that, it's going to do just more than that. So for instance, if we just wanted to do that, we're kind of running blind, because we don't really know if that voltage is actually producing, up here at the top, if that voltage is actually producing the frequency that we want. We would kind of be just guessing. So what happens is, it'll output its little signal here, and I'm not going to get really into the math of it, because in order to make it fit within the range that the chip works, you have to divide the frequency down, because it's so high. You know, this is in the tens of megahertz, and of course this chip doesn't like to operate at that level, so everything has to be divided down, similar to what we're doing with our Superheterodyne. It's the same kind of idea. We're taking a bigger, higher frequency and dividing it down to a lower one. But once we do that, we're going to take a sample of that frequency. It's going to come out of here as a sampled frequency, and it's going to get fed back into this chip. So you have your voltage going out. It's controlling the frequency of that oscillator. Then you're measuring that frequency, okay? And depending on if you're on AM or FM, this chip can handle both. So you have an input for the AM radio and an input for the FM radio, and depending on which one it looks at, it'll depend upon whether you have AM or FM selected. But the idea is, it's feeding back a sample of that frequency. This chip will then measure that and compare it to a reference. You see down here, we have a little oscillator circuit. And this oscillator circuit consists of a couple of components and a crystal, a quartz crystal. And it sets up a very precise and accurate frequency. It only makes one frequency. It doesn't vary. It's always one frequency. And on this particular unit, that frequency is 10.24 megahertz. So everything is compared to that 10.24 megahertz reference frequency. You following me so far? Clear as mud, isn't it? It'll get a little easier, don't worry. So if we look at a block diagram, here's that chip. And you can see that there are different things inside of here, okay? We have our reference oscillator, which was that circuit we just looked at, and it's being fed into this. And this divider circuit determines, this is the part, and you can see it's 1 divided by 2048 or 1 10/24, depending on if it's AM or FM. So you're taking that frequency and you are electronically dividing it into either a 5 kilohertz accurate reference or a 10 kilohertz, depending on if it's FM or AM. FM is looking at a 5 kilohertz signal, AM at a 10 kilohertz. And it all has to do with channel spacing and everything, because AM and FM is different that way because of the bands that they work in. But anyway, we have our controller from that other chip when we select our tuner up and down, and it goes into the programmable divider. This is the magic right here, is your programmable divider. It's all based on math, and it looks at these frequencies coming in. You can see they're being sampled from your oscillators up in your RF section. You can see coming into those two pins like we looked at earlier. And by doing that, it is always going to use this code to create a math formula that will always get our expected frequency, and it's dividing it down so that it will always equal the same as our reference, in theory, if it's right. So in other words, when we have our if we have selected our 90 megahertz down here, and it puts the code for 90 megahertz in here, it will set this divider circuit so that if there actually is 90 megahertz here, you will get exactly 5 kilohertz out of this divider. The next thing we have is called a phase detector. All the phase detector is going to do is it's going to look at this 5 kilohertz or close to 5 kilohertz, whatever it is. And it's also going to look at the reference 5 kilohertz that's always accurate and never changing. And it's not only going to compare the frequencies, but it's going to look at the phase between those. And if they don't perfectly line up, in other words, if the phases are different, then these frequencies must be different because they're not in phase, they're not in step with one another. So what that's going to do is it is going to change that voltage, and it is going to vary the voltage coming out until this frequency here equals this frequency. Once they do, we call that lock. Once it locks onto that frequency, it will hold that tuner at that frequency. And because this tuner actually uses this circuit both for the local oscillator as well as the RF, everything up here is controlled by that. In theory, this should be a really, really accurate tuner. And this was kind of like the big thing that they were promoting when these early digital tuners were coming out. That's the digital part. That word that's actually creating the divider that's changing the frequency to that standard 5 or 10 kilohertz. Okay? So that's how it works. So really, if you take the PLL and you take the digital word out of it, you still have a changing capacitor that changes the resonant frequency to change the tuning frequency of the radio. We're really not changing the principle of how radio works. We're just changing the principle of how we control it. Rather than having to rotate a knob that turns a capacitor and kind of keep it, you ever hear a frequency drift and you kind of have to turn the knob to get it back on, especially with AM. These don't do that because once they lock, they'll vary, they'll track, and it'll always kind of hold the frequency. So they're a lot more accurate. Things don't change as much, at least in theory. So because we have this loop of the voltage going out and then the frequency coming back, it's just this loop, okay? And it's always comparing the phase between the reference signal and our return signal or our sample signal, and it's always comparing the phase and trying to lock them together. We refer to this as a phased locked loop, or a PLL. That's how it works. It's really not super complicated when you break it down into the separate sections like that. It sounds really complicated, but it isn't. And a lot of these things you really don't have control over. This dotted line is an integrated circuit. You can't work on it, you can't fix it, you can't repair it. Either it works or it doesn't. And if it doesn't work, you take the chip out and you put a new one in. That's all. The main thing that we're always concerned with as people repairing these is the same kind of things that we worry about on an analog tuner. And that is this oscillating? Do we have a local oscillator? Do we have RF? Is there a signal here? And when we change our tuning frequency, does the frequency vary? If it doesn't, instead of trying to troubleshoot capacitors and things like that you used to, you're troubleshooting this voltage. Do we have our PLL voltage, and does it vary? You know, it's very easy to actually troubleshoot one of these, believe it or not. Now that we've gone through all this theory, let's break it down to the simplicity of it. One of the main things we want to look for is when we tune the radio and we change the tuning frequency, do we see this voltage vary, the VCO? The VCO controls the frequency, so theoretically, if we change our tuning frequency up and down, that voltage should go up and down with it. And most manufacturers make it very easy to troubleshoot this. So if we look our service manual here and we look through the theory of operation, you'll come to this table, and it's basically explaining, breaking down everything I just told you about the PLL chip. So for instance, if the input data, those pins, those 7 pins, if you have this pin here is a 1 and then everything else is a 0, and this is pins 3 through 9, then it's assuming that the receiving frequency is 88.1 megahertz. Your VCO frequency is 98.8, which is 10.7 megahertz higher than this one, right? So this will be our local oscillator. Our input frequency will be 2.47 megahertz, and that's coming in from that sample circuit. So we have that prescaler up here, which is taking that high frequency and dividing it down. On this particular one, it divides it by 40, and we comes out to here. So we should see that there, and the divider ratio, which is on that right here, that divider ratio on this particular one will be 494. We can take that number, and if you do the math, you'll find out that it'll come down to 5 megahertz if you divide that frequency. So just to give you an example, if that frequency is 2.47 megahertz, that would be 247,0000 hertz divided by that divider ratio, 494. You get 5,000, or 5 kilohertz. I'm sorry, I was saying megahertz. It's 5 kilohertz and 10 kilohertz, if you remember. And you can see if we go down the line and we divide these two numbers all the way down, depending on the frequency, it's always going to come out, these two numbers will always come out to 5 kilohertz. So that's a mathematical way of measuring these frequencies and making sure they're correct. Because if these frequencies are correct, this number will always be this. We have this selected, and when you divide it down, it will equal 5 kilohertz. And of course, if you remember, our reference oscillator is being divided down from the 10.24 megahertz into a 5 kilohertz, very, very accurate signal. If they match, we know we're locked in and that we're on channel, on frequency. If they don't equal, then the PLL circuit can move that voltage up or down until these match. And that's how it works. But if you notice, it's all automatic. So really, the two things when you're troubleshooting a PLL circuit like this, or these types of tuners, is this. And that is, you want to make sure that your VCO voltage varies when you adjust the stations, and that our pins, when we look at pins 3 through 9 here on this particular chip, that they equal that truth table. So when we look up that truth table, if we measure these pins, we can actually break down what they are. Now this one is actually not telling us the ones and zeros. Some of these charts actually do. They'll give you the ones and zeros. And you can actually measure each pin and see if it matches the frequency. Again, these will change as you adjust them. Okay, so we have the receiver up on the bench back again here, and we're going to go through and check the alignment and check the function of this thing. Now, just hooking it up to an antenna, I can tell that it's pretty much working pretty well. This is not the world's most sensitive receiver. I think the goal of this project, since it's such an early design, was to build a fully digital receiver, and they achieved that. Although at the time, the higher end analog tuners of the time probably would blow this thing away. And the main reasoning for that is, if you look at the way this thing's laid out, not a whole lot of shielding going on. Your lead lengths, there's a lot of little things that in a dedicated tuner, like for instance when we did the video on the old married couple with the TX9100, and when we did that TX9800, if you recall, there was a lot of shielding and things, and the layout was very meticulous. You don't really see so much of that on this one. However, this tuner is capable of performing fairly well. The other thing is it only has one stage of amplification in the RF section. So there's one RF amplifier, just that one little FET. But as we talked about earlier here, the first thing that you want to do is we want to check our reference oscillator, because if it's not accurate, nothing's going to work. Now, the problem you're going to run into on a lot of these receivers is if you just try to connect up a reference or your scope or your frequency counter or whatever, or spectrum analyzer, directly into the circuit where the reference oscillator is, it's going to either ground out the oscillator signal because it's so small and the impedance of your test equipment will actually kind of ground it out, or if nothing else, it will affect the frequency itself. So the bottom line is, connecting your test equipment right into the reference oscillator is pretty much a no-no. However, in this receiver, they actually have another way that we can actually test the reference oscillator in kind of a roundabout way. So if we look on this great big long board here, this is called the controller board, and this is the main brains, I guess you could say, of the tuner. And there's a big chip here. I think it's like a 40 pin or something like that. And this is a very special proprietary integrated circuit made by NEC for Radio Shack for this particular application. And we looked at it on the schematic. This is the one, that the IC402 it's called, and it's the one that's responsible for selecting the frequencies that we want. It's the one that's responsible for driving the display, setting up the code for the display so that the display can tell you what frequency you're on. It has the frequency counter in it for that. It uses, it generates that 7-bit word for the PLL synthesizer chip to tell it what to divide by to get the frequency you need. All these things are done with this chip right here. So one of the things it does is it has a clock that it has to have a very accurate clock in order to operate, and that clock just so happens to be 160 kilohertz. And if you take 160 kilohertz, how did they derive that number? Well, if you take the 10.24 megahertz of the reference oscillator, what it's supposed to be, and you divide that by the 160 kilohertz, you'll find that the number is 64. So the your PLL chip actually has a divide by 64 output on it, and that is how we're getting it. So technically, that 160 kilohertz is going to be a direct representation of the 10.24 megahertz signal, reference oscillator. And it won't get swamped down because it actually has a little higher output, and it has a capacitor decoupling it from the chip. So we can connect right onto that and measure that 160 kilohertz. And if we get 160 kilohertz, we know that our 10.24 megahertz reference oscillator is working properly. Now the place to measure it is they put these two little convenient posts here, and this is the one where the actual signal is going to be. This is a ground, and these don't show up on the schematic. In the service manual it talks about testing this, and you put a frequency counter on here, and it says to measure and verify that it's 160 kilohertz plus or minus 8 hertz. So they want it to be very, very accurate. So we're going to measure that now, and I have my probe here from my frequency counter. We'll get it hooked up, and we'll move over to the frequency counter, which is not working right now because I don't have the radio turned on. And let me get set up, and we'll turn it on and see what it says. Okay, the old girl's still working pretty good by the looks of it. If you notice, we're only off by 2.3 hertz. So I would say that's pretty accurate. We have plus or minus 8 hertz. So our little oscillator circuit is still working perfectly. So that's good news. Now, just in case, if that were out, there are two little 47 picofarad capacitors, and we'll look at this here. And we're looking at our PLL chip, and if you look right, here's your oscillator. These two little capacitors, the instructions basically say to just adjust those values if the frequency is off by more than 8 hertz. But fortunately, it's right on, and we're in good shape, and we can move on to our next test. Okay, the next thing we want to check on this thing is our VCO. Remember, we want our voltage. And once again, the service manual does give us a little direction on this. So if we dial in 90.1 megahertz, which I've done already, and connect it up to an antenna, to the antenna port, and we just want the tiniest little signal. And really the signal is not important for this portion. But what we want to do is we want to tune the front dial till it says 90.1 megahertz. So over here, I just tuned up and down until I hit 90.1 megahertz on the display, which is what we have. And then we want to take a voltmeter, and we want to connect to the ground and to our voltage for from our synthesizer. So there's the voltage for our VCO. And what they're saying is we want somewhere in the line of about 3.7 volts, plus or minus. All right. And we're going to use L5 to adjust that. So L5 is this coil right over here. And we want to set that to be about, and we're pretty close right now. We're at 3.5. So let's turn that and see if we can get it right on 3.7. There we go. And that's all there is to it. Now we're going to go down and we're going to check. We're going to put as small of a signal as possible. Should be somewhere in that 3 microvolt range, but because of the interference around here at certain frequencies, sometimes if there's some background noise on your bench, you may have to drive it a little tiny bit harder. But the idea is we connect onto the tape recorder outputs, the record out, and we go into our scope, and you should see your modulated signal. So we have 90.1 megahertz on our signal generator right here, and we're modulating it at 1 kilohertz FM, 75 kilohertz deviation. And we're going to adjust the 3 coils, and we're just going to try to see if we can get this signal as clean as possible. So here's number 1, and it looks like I'm pretty close. Alright, see how it gets kind of fuzzier? Alright, let's go to coil number 2. Wow. That cleaned it up. Very nice. And then coil number 3. And that one is pretty much on. Okay, so coil number 2 was out a little bit. And really what this directly affects is our sensitivity. So there you go. Okay. Now, basically the next thing you do is you go to a higher dial scale. On this particular stereo, I think they want 106.1 megahertz. And you do the same thing, except you adjust the little trimmer capacitor. So you adjust the coils at the lower end of the band, and you adjust the little trimmer capacitors at the higher end of the band. So you can see here was our 3 coils, 1, 2, and 3, and then the little tuning capacitors are right here, 1, 2, and 3. And then these other ones are our oscillators for high and low. And that's it. Set those, and we're basically gonna do the same thing at 106.1. Okay, we've gone ahead and we've done all the adjustments of the front end of the tuner, and you can see there that all those jittery lines there on our sine wave, that's interference, okay, from weak signal. And that's where we just start to be getting some static where you'd really hear it pretty well. And I'm doing that at 88.7 megahertz, which is clear at the bottom of the band almost. And I'm only driving it with 3 microvolts, and that's including the loss of the cables and, not including the loss of the cables and my little impedance matching box down here and all that. And we are still getting a respectable signal. Now, let's see if it tracks, because the whole idea is we want to be within 1 microvolt of getting that same signal all the way at the top and all the way at the bottom of the band. So let's drive it up and see. So we're going to go to our frequency, and we're going to go to 107.1 megahertz. And let's dial up to 107.1. Wow, look how solid that is. And if I go down, clear down to 2 microvolts, we just start to see the little bit of interference there. So there's about a 1 microvolt, and you're going to find that out is that the bottom of the band is a little bit more susceptible to noise than the top of the band. So if you get about a 1 microvolt difference between your low frequency and high frequency FM, you're doing pretty good. So actually this tuner, for only having 1 gain stage in the RF and not having a whole lot of shielding, is doing pretty well. So to recap, so far what we've done is we have set our VCO voltage to track at a high point in the band and at a low point in the band. Okay, so like at 90.1 megahertz and 106.1. And then we adjusted these little trimmers here, both between the coil and the capacitor, for high and low band, and made sure that they're all tracking together at the proper frequency. So when we put that voltage into these varactor diodes, these little adjusters here are just making sure we're kind of nulling out any of the imperfections of these themselves. So that's what we've done so far, and that takes care of all the RF. Now so far all we have is RF and our mixer. Now after those get mixed together, that's going to drop down to our 10.7 megahertz, and it is going to go down here to our IF section, or intermediate frequency. And from this point on, as far as FM radio is concerned, everything's going to be based on 10.7 megahertz. It's all going to track at that. So we're going to set that up next. Okay, so just like on any other tuner we've done, first thing we want to do on FM when we're going to go do the IF section is to adjust the discriminator. And then you can always kind of tell the discriminator because it always is kind of like this big aluminum can like this, and it doesn't look like all the other adjusters on the board. So we want to do the primary, which is, there's actually 2 slugs and 2 coils inside this tall can, and we actually want to have a special tool like this that can actually go through the one on the top and reach the one on the bottom. And we want to connect our meter to 2 test points, which is TP2, we want our plus to be, and TP1, which is here, we want to adjust. Sorry, I'm hitting the camera because I'm actually working around the camera. And we want to measure our voltage, and we want to go, here's our top of the coil. We want to actually go down through it and kind of get into the bottom coil, and we want to adjust it for about 30 millivolts is what the service manual is saying. So let's see if we can get 30 millivolts on here, because we're off a little bit, I see. So let's see here what this does. Well, that definitely does do something, huh? Wow, this is super duper touchy. Don't move. Okay, we're pretty close, and I think that's where I'm going to leave it right now. I don't know if I can get it dead on 30. You know, you always try to get that little bit more out of there. I think that's just where it's going to sit. So we're within 1 millivolt. That's good. Okay, so let's see what we do next. Okay, the next thing we're going to do is we're going to adjust now this top coil. And again, this is no different than all the other tuners out there, the analog ones and so forth. The top slug we're going to actually adjust for minimum distortion. Now, you can kind of do this by ear, but it's impossible to get it perfect. If you have a distortion meter, that's kind of the best way to do it. And it doesn't matter if it's, we can use a, well, I'll show you. You can use a digital distortion meter like I'm using here. You can use one of the old analog distortion meters like that one, like the Leader LDM 171, or you can even use the computer-based software one in your sound card. And there is software that I think I showed you all in the past. But we're just going to use this because it's just easy to hook up for me. And we're already sitting at about 0.3% distortion. So let's see if we can make that a little bit better. We may or may not. So that's going up. So let's go the other way. Oh yeah, it's coming down. Oh, went through it. So about 0.1 is right about where we're going to kind of max out at. Very touchy on these. Okay, so about 0.15. So we did make some improvement on that. That's good. Now, if this were not adjusted properly, what would happen is that's where you start hearing that sibilance and that kind of chuffing noise when you are listening to a station. The bass will tend to get distorted sounding, and this is one way that you can ensure that that's not going to happen. This one's going to sound really clear because you can see the distortion's pretty low. And remember, you can have the lowest distortion in the world on your amplifier, but if your tuner doesn't have low distortion, it's just the chain is only as strong as its weakest link. And that's something that you need to remember when you're working on all these things. So, and again, unless you really have to start getting a lot more consideration in your design of your shielding and circuit design to get that to go down even more. And that's the difference. The little differences is what makes the huge difference in performance on the on the much higher end tuners and so forth. So this one looks like it's pretty much peaked out, so let's go to our next step. Okay, as you can see, we're now going to go to the middle of the dial, 98.1 megahertz. We're going to put a weak signal in now. So we had a very strong 1 millivolt signal to do the discriminator circuit. But now we're putting a tiny, teeny little signal of 3 microvolts, and just enough to get kind of a noisy signal to come out. And then we're going to go down back to our front end board, and we're going to set our IF can, which is this little transformer here, T1, and we're going to adjust that till we get maximum amplitude on our meter and best looking signal on our scope. So here we go. Sorry about everything moving around. Let's adjust it and see. There we go. And you can see that cleans it right up. Right about there's where it's cleaning up. I think that's it. Nice. So that was off too, a little bit. Every little bit adds up, you know. As they say, when these things are each thing being out a little tiny bit, it's kind of like death by 1,000 cuts. So we want to make sure we adjust this thing. You know, you get every single adjustment as accurate as possible, and then that ensures that the tuner is going to perform at its top possible rate. Now, one more quick note. To make this adjustment, I actually used a very long adjustment tool and kind of stood way back away, because watch what happens when I walk close to the tuner. You see what's happening? It actually gets more interference, and as I walk away, just moving around it, you could see affects it. So you want to kind of stay away from this thing because it's all open when you do this. Some of the higher end tuners actually have shielding that attaches over all these boards to prevent that from happening. And you actually have holes kind of like just on this front end board. All of this would be covered with that, and you would go through the holes to adjust it. It has a lot less interference because of that. So it can be fidgety, and you just kind of have to fiddle with it and get it just right. It takes some time, but just if you're patient, you can get it to come in. And here we go. So you can hear there's a lot of static because I don't get very many stations down here in the basement at the bottom of a hill, but not bad. It wouldn't pick this station up very well before we aligned it. So don't want to get flagged here, but all right. Okay, I'm going to end this right here because really the rest of the alignment, you know, adjusting the meters and things is the same on every tuner, you know, the ones that we've done a whole bunch of. I just kind of wanted to go over some of the idea of adjusting a PLL synthesized tuner versus a analog tuner. And really the only differences are the ones we just looked at. And you can see it wasn't that much different. So I hope this helped you all out, especially a lot of you who are new to this hobby. I really want to inspire you guys to do this because it's a lot of fun. I really enjoy it. I get a lot of relaxation and enjoyment working on these things. And I hope by sharing this with you, you guys will find enjoyment in this hobby as well. So again, it's Christmas Day, and just enjoying my day off a little bit here, and of course everything goes back to the craziness tomorrow. So I wish you all once again a Merry Christmas and a Happy New Year. I wish you all peace, joy, happiness, and good health in your lives. I really mean that. And till next time, take care and stay well, and let's work on some radios.